Welcome, everyone. Over the next 35 to 45 minutes, we'll walk the arc of exploration, from empirical Stone Age quarrying to a closed-loop, AI-driven subsurface intelligence system. The paradox we'll resolve is this. In an age of unprecedented instrumentation, mineral discovery has become slower, riskier, and more capital-intensive. Our goal is to make that paradox explicit and then show a practical path to faster, cleaner, higher certainty decisions. We'll cover the genesis of exploration, the industrial and analytical revolutions, the modern toolkit era, and finally how IRIS-X compresses months into days by eliminating laboratory bottlenecks and minimizing footprint. Let's begin. In prehistory, exploration wasn't measurement, it was recognition. Humans selected obsidian, flint, and ochre by color, luster, conchoidal fracture, and tactile response. Trade routes became proto-prospecting datasets. If a village had obsidian blades, you inferred supply chains and source terrains. The failure rate was enormous because no systematic methodology existed. But two enduring ideas were born. First, materials encode provenance. Second, movement of goods reveals hidden geology. Those themes echo throughout the history we're about to trace. Ancient civilizations introduced the first engineering layer, adits for drainage, ventilation shafts for safety, and planned stopes for extraction sequence. Ore quality assessment still relied on visual heuristics and rudimentary fire checks, but state-level planning created repeatable workflows, proto-mine plans, labor organization, and material accounting. The universal constraints were in flowing water and limited depth. Engineering increased capacity, but did not yet provide clarity on where to dig next. In the Roman world, hydraulic mining harnessed controlled water to break and move material at scale. In Han China, deep shafts and mechanical lifting extended vertical range. Standardized tools and record-keeping introduced the concept of repeatability, the earliest hint of process control. Yet the fundamentals lagged. No gas detection, limited understanding of rock mechanics, and coarse control of water. Scale increased, but subsurface certainty didn't. We'll see this capacity not equal certainty gap recur until we reach modern sensing. The Renaissance converted tacit craft into documented method. Metallurgical recipes, furnace designs, and early textbooks, like De Re Metallica, codified repeatable procedures. Codification accelerated training and diffusion of practice, and it seeded the core of today's QA/QC mindset. Define a process, teach it, audit it. For exploration, this meant better planning and more consistent execution, but still limited predictive power underground. Gunpowder and black powder increased rock breakage rates by an order of magnitude, shifting the economic calculus of extraction. But ventilation, gas detection, and geomechanical understanding lagged, so accidents and uncertainty rose. This is the historical pattern. Extraction speed often outpaces characterization. It's the first time we clearly see a theme that persists into the data-rich present. Velocity, without clarity, amplifies risk. The rushes of the 18th and 19th centuries surfaced the first systematic signal-to-noise problem. Camp geology and biased sampling generated anomalies everywhere, while gold price volatility pulled capital into geologically look-alike terrain with low probability of success. The phenomenon of false positives became embedded. Visual similarity and anecdote were mistaken for mineral system continuity. This is the origin of a pathology that still drains budgets today. Steam hoists, pumps, and improved ventilation expanded depth and increased productive hours. Systematic underground surveys created better maps and the first planning feedback loops. Yet the key exploration problem remained: the selection of location. Mechanization solved how to mine, not where to mine. That gap keeps resurfacing until we couple sensing and decision-making in near real time. Stratigraphy and structural geology introduced predictive frameworks, correlations across stratigraphic packages, the role of faults, folds, and intrusive contacts, and the emergence of ore deposit models. Maps evolved from documentation to decision tools. The discipline shifted exploration from descriptive mapping to interpretation-led targeting, still heavily human-driven and still slow. Fire assay and wet chemistry delivered the first standardized precision, and nascent QA practices standards, blanks, and duplicates appeared. But labs created new pacing items: sample transport, chain of custody, queue time, and eventual reporting. Precision improved, timelines lengthened. Decisions often waited on trucks and spreadsheets rather than geology. Magnetics and gravity added an unprecedented screening capability. Early seismic added structure. These methods excel at collapsing large search spaces, but resolution and inversion ambiguities limit where exactly. The discipline thereby learned the difference between regional rank ordering and precise target delineation. Integration with other evidence streams would become essential. Aerial imagery exposed lineaments, drainage anomalies, and alteration tones invisible from ground level, transforming access planning and trench placement. But interpretation subjectivity remained high. Two experts could read the same photo differently. The enduring lesson: seeing patterns is not equivalent to understanding causation. Soil and stream sediment programs brought thresholding, background characterization, and pathfinder relationships into routine practice. With statistics came algorithmic anomaly detection, but environmental confounders, weathering, terrain, contamination, introduced persistent false positives. Context began to matter more than standalone data points, another impetus for multimodal fusion. Core and RC drilling deliver ground truth. QA/QC matured into rigorous protocols governing sampling density, analytical precision, and interpretation. The trade-off became explicit. Certainty demands time and capital. Depth, rig time, and analytical cues began to dominate budgets. The modern dilemma was set: how to get truth with less drilling, less disturbance, and less delay. Multispectral and hyperspectral satellites revealed alteration and system footprints at regional scales, with spectral indices tied to mineralogical change and hydrothermal halos. Cloud cover and resolution initially constrained impact, but when fused with geophysics, performance leapt. Integration, rather than single-modality reliance, emerged as the operating principle. GIS made spatial databases, kriging, weights of evidence, and prospectivity modeling daily tools. Data hygiene improved dramatically. Visualization improved communication. Yet the decision cadence remained slow. Multi-month cycles dominated by manual interpretation and sequential workflows. We organized better, we did not decide faster. Environmental baselines for water, air, biodiversity, and community impact became non-negotiable. Stakeholder consultations and social license reordered the critical path. The mandate was clear: reduce footprint without reducing certainty. Traditional reconnaissance, roads, pads, heavy mobilization became harder to permit and slower to execute. Low-impact sensing moved from nice to necessary. Drones, portable XRF, automated core logging, and advanced processing promised real-time exploration. Reality: siloed datasets and interoperability gaps, with laboratory queues still pacing decisions. Big data became vernacular. Big latency remained the field experience. The lesson: instrumentation is not a system. Despite more data, discovery costs rose sharply after 2000. Three bottlenecks explain most overruns. Multimodal noise inflates false positives, human interpretation bandwidth does not scale, and laboratory throughput stretches decision cycles into months. The urgency is plain. We need real-time, in-situ certainty that sidesteps labs and suppresses noise at the source. Our design spec crystallizes into three goals. First, real-time sensing with minimal disturbance, continuous measurement that eliminates lab cues. Second, automated data fusion to cut human bias and recover weak but consistent signals across modalities. Third, deterministic timelines, campaigns measured in hours and days, enabling rapid go, no-go. These are not buzzwords. They are engineering requirements. IRISX is a continuous closed-loop sensing architecture. Controlled nitrogen injection carries engineered nanobiomarkers through precision radial wells. These markers bind selectively to target minerals and gases. The returning carrier stream is captured by surface arrays for real-time detection and magnetic tracking, and an AI decision engine fuses all signals into confidence-rated actions. The core innovation is tight coupling: inject, bind, return, detect, decide, without a laboratory in the middle. Radial wells transform coverage economics. A single hub pad orchestrates multiple spokes, each controllable in flow, pressure, and pulse timing. Campaigns synchronize across the network, increasing sampling density while reducing access roads and dozer work. Infrastructure efficiency becomes a sensing advantage. More rock volume interrogated per square meter of surface disturbance. Here's the logistics shock. A conventional grid requires numerous pads and roads to touch the same subsurface volume. Iris-X reaches that volume from far fewer surface locations using radial reach. You achieve equivalent, or better, geological coverage with dramatically less disturbance. That shifts permitting timelines, reduces mobilization cost, and accelerates the first decision point. Multi-element MOS tiles form our surface chemical intelligence. Each tile integrates engineered sensing films, microheaters for response optimization, and environmental compensation to maintain stability under field temperature and humidity swings. Telemetry is encrypted end-to-end for remote calibration and monitoring. The point is continuity. We replace batch sampling with continuous, high-fidelity measurement at the surface. Nitrogen is the right carrier for 3 reasons. Chemically, it's inert, no reactive interference with targets or biomarkers, so signals are clean. Operationally, it is non-toxic and non-flammable, simplifying safety and environmental risk controls. Quantitatively, precise flow control allows us to model delivery and recovery, turning transport into data, not noise. Carrier selection is not a detail. It sets the analytical ceiling for the entire loop. Fluxgate magnetometer arrays resolve minute signatures associated with our markers as they traverse fractures and permeable pathways. By synchronizing detection with injection pulses, we separate target responses from environmental background. The result is a live 3D view of subsurface highways, how carriers move, where they accumulate, and where the binding occurs. Traditional workflows generate many anomalies with uncertain meaning. Pathway-aware tracking flips that logic. We prioritize interaction strength and convergent pathways over mere presence. Targets are ranked by quality, not quantity. In practice, that translates to fewer lookalike false positives, tighter trenching windows, and a smaller set of confirmatory drill holes with higher conversion. Our AI stack ingests surface chemistry, magnetic path lines, operational parameters, and contextual geology. It produces explainable, confidence-rated recommendations, go/no-go, where next, and with what intensity. Crucially, the models learn from outcomes, so each campaign improves the next. This is how we move analyst hours from data wrangling to decision quality control. Iris-X is not a walled garden. We fuse satellite/drone imagery, legacy geophysics, historical sampling, and drilling databases with real-time measurements. Role-specific dashboards put the right view in front of ops, geology, and ESG stakeholders. Exports to mine planning and CAD environments ensure the exploration to development handoff is direct. Integration is how you monetize legacy data, not just store it. Quality in IRISX is continuous, not periodic. Automated calibration checks reference signals for drift, environmental compensation maintains precision under thermal and humidity excursions, and all operations are logged to an auditable trail for regulatory defense and root cause analysis. The effect is simple. You trust measurements because the system demonstrates its own stability in real time. The system is engineered for field reality. Wide temperature and humidity ranges, EMI, hardened sensing, low continuous power compatible with solar/battery, and satellite comms for remote control. We've operated in alpine, arid, and tropical settings with consistent performance. This matters because deployment agility often determines whether geology or logistics dictates your schedule. Engineered nanobiomarkers produce distinctive signatures for REE and actinide systems that conventional methods struggle to separate in the early reconnaissance phase. Real-time anomaly ranking narrows trenching to the few highest confidence zones, and confirmatory drilling becomes surgical rather than gridded. The objective isn't to eliminate drilling, it's to elevate the value of each hole. With fewer pads and roads, controlled radial access, and consolidated equipment, disturbance drops significantly. Continuous sensing provides defensible environmental baselines and ongoing monitoring, improving permitting posture and community relations. ESG moves from a compliance overhead to a strategic asset, speeding approvals while strengthening social license. Iris-X compresses the path from mobilization to decision. When you remove laboratory cues and replace batch sampling with continuous signals, the critical path collapses. Think on the order of weeks to days. Faster decisions create option value. You can test more targets, iterate with live feedback, and reallocate capital dynamically as the subsurface story clarifies. Here's the cadence. Days 0 to 2. Satellite/GIS pre-screen and hub pad selection with access and environmental constraints built in. Days 3 to 5. Mobilize, drill radial spokes, deploy arrays, minimal disturbance. Days 6 to 8. Synchronized nitrogen injection, circulation, and multi-sensor capture. Days 9 to 10. AI confidence maps, ranked targets, and a short list for confirmatory drilling. Sprints, not seasons. We connect to your data lakes and planning software via APIs. Teams use role-based dashboards. The single pane consolidates operational state, anomaly confidence, and ESG metrics. Enablement is counted in days, with runbooks that let your crews operate without babysitting the stack. Adoption friction is designed out, so value shows up in the first campaign. Every recommendation carries uncertainty bands, and anomalies are clustered into families to identify systematic behaviors and suppress one-off noise. Historical deposit benchmarking contextualizes confidence scores, helping executives tune risk appetite to deposit style. Decisions become defendable because we quantify doubt, and then we act on it explicitly. IRIS-X is a platform, not a point tool. Near-term, deeper tracking and expanded mineral libraries. Mid-term, basin-scale coordination, autonomous modes, and environmental surveillance overlays. Long-term, federated AI, predictive geological modeling, and national-scale subsurface intelligence networks. The same infrastructure that accelerates discovery doubles as a monitoring fabric for environmental stewardship. On day 1, 3 things change. Speed. Decisions move from months to days, enabling portfolio agility. Certainty. Fewer false positives and explicit confidence bands improve capital efficiency. Footprint. Minimized disturbance accelerates permitting and strengthens community relations. Engineering teams, CFOS and ESG, leads all see tangible deltas in their own metrics. Fast. We've validated IRIS-X in the field, including a pilot in Padang, Indonesia, demonstrating rapid, certain, and environmentally responsible outcomes in challenging geology. The next step is straightforward. Align on a pilot scope, agree on KPIs and data governance, and schedule deployment. Let's co-design the first 10-day sprint and put this system to work on your ground.